Welcome back, everyone. This is going to be the second lecture in Chapter 30. In this lecture, we're going to focus on the magnetic force between two parallel currents. So if you have two wires that are next to each other, they're actually going to experience a force on each other. So we're going to talk about that today. The learning objectives for today are going to be to explain how parallel wires that are carrying currents can attract or repel each other. Then we're going to define the ampere and describe how it's related to current-carrying wires. And also we're going to calculate the force of attraction or repulsion between these two current-carrying wires. Right? So we're going to see kind of how it happens, and then also we're going to come up with a calculation to do this. So before we get started, I just want to remind everyone from the previous lecture, we used the Beer-Savart law, and we developed an equation for the magnetic field that's produced by a current-carrying wire. Right? So when you have a wire, you have charge running through it. Basically, moving charge is going to create a magnetic field. So that's what we looked at, and that equation that we found is given by this expression. So the magnetic field is going to be equal to U naught times the current divided by 2 pi r. And if you remember, we said that U naught is the permittivity or the permeability of free space. And this is just a constant that we're going to use in our equation, right? The value never changes. It's always equal to 4 pi times 10 to the negative 7 Tesla meters over amperes. All right, so let's take a quick look at the pictures we have here on the left side. So I was talking about, when you have this current-carrying wire, it's creating a magnetic field. That magnetic field, we know we can use the right-hand rule to determine. We put our thumb in the direction of the current, so in this case it's sort of towards the top of the page. And then our fingers kind of curl around the wire and show you the direction of this magnetic field. That kind of creates these concentric circles around the wire. As we get further away from the wire, we know that the magnetic field is going to decrease, right? Just sort of like an electric field would decrease. And that's shown here in the equation, right? If you increase the radius from the wire, you're decreasing the magnetic field. All right, so now we're going to introduce this second wire. We're going to call this I2. So the first one we'll call I1. The second one we'll just call I2. It's now in the magnetic field that was created by I1. Right? Now it is in and of itself creating its own magnetic field, right? But that magnetic field that I2 creates is not affecting I2. It would only be affecting I1. So we're going to look at how I1 affects I2, and then basically I2 would also do the same thing to I1 or something similar. All right, so that's the idea. The second picture over here just shows you sort of a top-down view, a bird's eye view of the situation. If you're looking down these two wires, right, so you have I1 here, you have I2 there, you can see that the magnetic field is being produced by I1, and it's hitting I2 right here. So it's sort of perpendicular to the direction. We're going to talk about what that force is going to look like over here on the next page. All right, so I just took that same image and I copied it over to our second page. Let's go ahead and take a look at what the force that's actually acting on this wire is going to be. So from our previous lectures, we had an equation for the force on a current-carrying wire, right? This is going back to last chapter. So let's start with that. All right, that was equal to ILB sine theta. Okay. This is assuming that, right, you have a specific length of wire, you have a specific magnetic field, you have a current, right, so on and so forth. So let's go ahead and apply this to our situation here for the force that's on wire 2. So the force on wire 2 is going to equal, the current of wire 2, right, as is in the equation, times the length of wire 2 multiplied by that external magnetic field that it's experiencing. And that sort of external magnetic field is coming from the I1, right in the center. It's coming from that current. So I'm just going to, well, for now, we'll just put in, right, the magnetic field from 1. Okay, well, if I take the result of the magnetic field due to a long current carrying wire that I showed you on the previous page, we can put these two things together. So F2 is going to be equal to I2 times the length of the wire multiplied by the magnetic field produced by the current 1. So that's going to be mu naught I1 divided by 2 pi r. Okay. Now I'm just going to simplify this a little bit, and I also want to make it a little more general because this would be the specific force that a wire is experiencing. Sometimes you don't know the length of the wire. Sometimes it's like an infinitely long wire. So generally how you would write this is you would take this length and put it over on the other side of the equation, and you would solve for the force per unit length. Right, so we're going to simplify this by dividing the L to the other side. We'll simplify the right side, so it's mu naught, which is the permittivity of free space, times, the permeability of free space, times I1 times I2, divided by 2 pi r. And again, what we've identified here is the force per unit of length. Right, so depending on how long your wire is, you can then determine what the total force is, if you know what the force per unit length is already. Right, so notice how we have both of the currents matter in this situation, right? In both cases, you have I1 and I2. You have the radius, which is just the distance between those two wires, right? That's shown here. And then you have the permeability of free space. All right, so now that we have the equation that we can use to find the force, I want to look at the direction of the force, right? And we're going to use this example to do that. Are these wires getting pulled together? Are they getting pushed apart? Are they kind of going in or out of the page? I want to take a look at that. So we'll use the example to show that. It says 2 long current carrying straight wires are parallel and 10 centimeters apart. One carries a current of 2 amps and the other carries a current of 5 amps. If the two currents flow in opposite directions, what is the magnitude and direction of the force per unit length of one wire on the other? Right, and then we're going to do the same thing, but we're going to see what if the two currents are going in the same direction. So let's start off with part A, which is sort of defining the directions of the currents as opposing. So we'll draw one wire, let's say in this direction, we'll call that I1, and then we'll have a second wire, we'll call that I2, going in the opposite direction. So these are in the same plane. They're just opposing. They're essentially anti-parallel to each other. Okay, so we know that the distance between them is 10 centimeters, so we'll just go ahead and write this distance as the radius. We'll go ahead and write down our givens for the problem. So the radius is going to be 10 centimeters, which is 0.1 meters, right? I always try to write things in standard units. The current 1 is going to be 2.0 amps, and current 2 is going to be 5.0 amps. The first thing they're asking us to do is just find the magnitude of the force per unit length, and then of course we'll find the direction after that. So let's go ahead and write out the equation for force per unit length from the previous page. So that's going to be mu naught I1 I2 divided by 2 pi r. Putting in our values, our permeability of free space is 4 pi times 10 to the negative 7. I1 is 2 amps, I2 is 5 amps. And then we'll just divide by 2 pi times the radius, 2 pi times 0.1. All right, we throw this into our calculator, and you should get 2.0 times 10 to the negative 5 newtons per meter. Okay, so now we have our result. We'll go ahead and box our result. 2.0 times 10 to the negative 5 newtons per meter is the magnitude of the force. But of course, we also want to figure out the direction of the force. So we're going to figure out the direction by using our right-hand rule, as you can imagine, as we've done so far already. And I want to look at essentially the original equation, right? Thinking of that force is equal to I L cross B equation. So I want to know the direction of L, which is the direction of the current, and I also want to know what the direction of the magnetic field is that's acting on I2. So let's focus on I2 first. All right, so if the current for I1 is downwards, right, if the current's in this direction, to figure out the direction of the magnetic field that I1 creates at I2, you're going to use the right-hand rule. So you put your thumb in the direction of I1, and then you curl your fingers around, and you'll see that the magnetic field at I2 should be coming out of the page. All right, so the magnetic field over here is going to be coming out of the page. I'm just going to draw it with the symbol that represents out of the page. All right. So now that I know the direction of the magnetic field that's acting on I2, I can use my right-hand rule to figure out the direction of the force. So I put my fingers in the direction of the current first, right, which is the length vector. So that's going to be up towards the top of the page. And then I curl my fingers out of the page, which is kind of towards me, out of the page, and my thumb is pointing to the right. So the direction of the magnetic force is going to be to the right. Let's do the same thing for the I1, right? Because the same idea is happening. I2 is creating a magnetic field that's causing I1 it's causing it to move because it has a force being applied to it. So let's do the same thing. So if I2's current is up towards the top of the page, I'm going to put my thumb in the direction of I2. And then I'm going to curl my fingers around, and I see, as I do that, the magnetic field at I1 is also out of the page. So we're going to have out of the page here as well. Okay. So now let's find the force. Again, using the right-hand rule. So my fingers are pointing down in the direction of the current. Then they curl up out of the page. And when I do that, my thumb is facing to the left. So there's also going to be a magnetic force on this wire to the left. Okay, so you can see what's happening here. You have essentially an equal and opposite force that's causing these two things to push apart. Right? So you have one pushing to the right, one pushing to the left. So you end up with a repelling force. Right? Instead of saying, you know, left, right, up, or down, I would definitely say it's a repulsion or a repelling force because they're pushing each other apart. Okay, so that would be our solution to part A. Now, for part B, it's asking us what is the magnitude and direction of the force per unit length if the current flows in the same direction, right? So it's a different setup here. Let's go ahead and draw both of these downward. So the currents are in the same direction, so that's going to be I1, that's going to be I2. I kind of want to do the same thing. Now, none of the values are going to change here, right? You're still going to get the exact same thing. So the force per unit length is still going to be 2.0 times 10 to the negative 5 newtons per meter. That's not going to change. Let's go and see what's going on with the directions. So again, I want to use the left wire on the right to see how it's creating the magnetic field. So if I put my thumb in the downward direction for I1 and curl my fingers around to I2, I see that my fingers are pointing out of the page at I2, right? This is the exact same thing we did last time, so we would expect this not to change. So you have an outward electric field. I'm sorry, magnetic field, excuse me. Now, for I2, so I2 is going down. You're going to put your thumb in the direction of I2, and when you curl your fingers around this wire of current, you see that your fingers are pointing into the page at I1. So since they're facing into the page, you're actually going to have a magnetic field in like that. Okay, again, you're going to use the right hand rule on I1. My straight hand rather, is going down. I am going to curl my fingers into the page when I do that, and my thumb is facing to the right. So I have a magnetic force to the right. Now looking at I2, again, my fingers are pointed down. I'm curling my fingers out of the page, and my thumb is now inwards. Okay, so when the currents are going in the same direction, you have an attraction force. When they're going in opposite directions, they're going to be repelling each other. Right? That should be the same for any case, as long as you're looking at two parallel wires that are going in the opposite direction or in the same direction. The result for the directions should be the same. Okay, that's all we have for this lecture. We'll be continuing on next lecture and talking a little bit about Ampere's law. See you next time.